Dear friends, welcome to this channel. In this video, I will discuss the questions from 21 to 30 in JAM 2020 chemistry paper. Question number 21, the complex which does not obey 18 electron rule is. Here complexes are given. The first complex CO2CO8. The structure of CO2CO8, one of the structures of CO2CO8 I am taking. This is a structure. Each CO is connected with 4 CO ligands. Four CO ligands. So you have to count the total number of electrons on the metal atom after formation of complex. Let us take this part. Here, metal cobalt. What is the oxidation state of cobalt? Here, all the ligands are neutral ligands. We know that carbon monoxide is a neutral ligand. So, the charge on the cobalt will be 0. So, what is the electronic configuration of cobalt? 3d7 4s2. So, the number of valency electrons will be 9. So, from cobalt we will have 9 electrons. From ligands, how many electrons? From ligands, you have 4 CO ligands, so you will get 4 into 2, 8 electrons. And here there is a metal-metal bond, one metal-metal bond. From one metal-metal bond, you will get 1 electron. The contribution of a metal-metal bond will be 1 electron. Finally, you will get 18 electrons. So, in this complex, each cobalt attains 18 electrons after formation of complex. So, this one above obeys 18 electron rule. Let us take this one, FeCO4 2 minus. Here the complex has -2 charge, and let us take the charge on X is iron is X and force into 0. CO is a neutral ligand. So finally you will get X is equal to -2. If you take iron, what is the electronic configuration? The configuration will be 3d6 4s2. So in elemental state, the electrons will be 8, and 4 CO ligands. 4 CO ligands, you will get 8 electrons, and -2 means you have extra 2 electrons. So finally 18 electron. So this one also obeys the 18 electron rule. Let us take this complex. The total charge on the complex is 0. Let us take the charge on the manganese as X, and here H is a negatively charged ligand, H minus, so -1 charge, and 5 into 0. So finally you will get X is equal to +1. So the oxidation state on manganese is +1. Then what is the electronic configuration? The electronic configuration is 3d5 4s2. 3d5 4s2. So from manganese you will get 7 electrons. From hydrogen you will get 2 electrons, and 5 COs you will have 5 into 2 10 electrons, and here there is a positive charge, you have to remove 1 electron, so -1, this is -1. So 9 19 -1, it will be 18. So this one also obeys 18 electron rule. Let us take this complex. Here cyclopentadienyl anion, the charge on cyclopentadienyl anion ligand is -1, chlorine is -1, monoxide is 0, and ppH twice is -1. So what is the charge on ruthenium? Let us say X. The total charge on complex is equal to 0. So x plus minus 1 plus minus 1 plus minus 1. So finally you will get x is equal to plus 3 oxidation state. On ruthenium, what is oxidation state? Plus 3. And here C5H5 minus 1, it can donate 6 electrons to the ruthenium, and chlorine 2 electrons, CO 2 electrons, and PPH twice also 2 electrons. So finally, how many electrons will be there on the ruthenium? We know that ruthenium belongs to iron family, iron, ruthenium, osmium. So in iron family, you have D6 n minus 1 D6 S2 configuration. So you have 8 electrons. And ruthenium, how many electrons you have? 8 electrons. And from C5H5 minus 1, you will get 6 electrons. From 3 monodentate ligands, Cl, CO, PPH twice, you will get 3 monodentate ligands. You will get 3 into 2, 6. And what is the charge? What is the charge? The charge is plus 3. You have to remove the charge. So minus 3 it will be. 8 plus 6, 14, 14 plus 6, 20, 20 minus 3, 17. So in this complex, the ruthenium has 17 electrons. So which one is the correct option? Option D is the correct option. The solid state structure of HF is, okay, in solid state, hydrogen bonds are given. In between HF molecules, the intermolecular forces are hydrogen bonds. These are hydrogen bonds. In solid state, the hydrogen bonds are non-linear. The first point is these are non-linear. So this one is not correct. These are linear bonds. And the second one is that the angle, the hydrogen bond makes some angle. Suppose if you take this one, F, H, F, here there is a hydrogen bond. This one has some angle. F, H, F, H, F, H, here also some angle. Okay, in all these cases, the hydrogen bond makes some angle. Okay, in this case also, the hydrogen bond makes some angle. But if you take this structure, if you take this structure, the fluorines are far away. The arrangement of fluorines, this one is far away, this one is far away, and this one also far away to each other. In this case, very close. These two fluorines are very close. In this case also, these two fluorines are very close. So there is a repulsion between these fluorines. So when compared with the C and D, their structure B is more stable. And another point is that when fluorine, hydrogen and fluorine, all these are on same line, there is a strong bond between strong hydrogen bond between fluorine and hydrogen. Suppose if we take this structure, fluorine, hydrogen and fluorine, these are not on the same line. In this case, the hydrogen bond is very weak. So which one is the correct option? B is the correct option. The number of DD transitions expected for the complex CuNH3 twice H2O4 2 plus. Okay, in this complex, what is how many number of DD transitions are possible? It's a octahedral complex. Octahedral complex. What is the electronic configuration of Cu? Here, the oxidation state of Cu is plus 2. Here, the total charge is plus 2, and let us say X. The charge on copper is X, and here NH, ammonia and H2O, both are neutral ligands. So it will be 2 into 0 plus 4 into 0. So X is equal to plus 2. So, what is the electronic configuration of Cu2 plus? The electronic configuration will be 3d8, 3d9, 4s, 0. This is the electronic configuration of copper in this complex. Suppose if you take this complex, the d orbitals will be split into T2z and Ez. Okay, T2z set of orbitals. This is the dxy, dyz, dzx, and this is dx square y square, dx square y square, and dg square. What is electron configuration? D9. You can feel electrons 1, 2, 3, 4, 5, 6, 7, 8, 9. Here, this one T2G6 and EG3. EG3 is asymmetric electronic configuration. It's not symmetric electronic configuration. When the molecule is non-linear, octahedral geometry is a non-linear, and when the electronic configuration is asymmetric, then there is a concept John Teller distortion, JT distortion. Okay, in John Teller distortion, there is a losing of degeneracy. Here there is a Z out complex will be formed. So in Z direction, the ligands will be very far away from when compared with the XY direction. So the orbitals in Z direction will be stabilized. So these three will be further split into this one is dxz, dyz, and this one is dxy. And in this case also there is a further splitting. There is a losing of degeneracy. This one is dz square, and this one is dxy. Okay, when Z out complex is formed, suppose this is octahedral geometry. This is the octahedral geometry. This is in Z direction there is elongation. So this is the distance. In XY direction, very close to the metal. The ligands are very close. So when ligands are very close to the metal in XY direction, the orbitals which are in XY direction will be repelled and will be destabilized. In Z direction, the orbitals will be stabilized. So here you have to fill the electrons. 9 electrons you have to fill. 1, 2, 3, 4, 5, 6, 7, 8. This is a 9. So how many transitions are possible? This is one level, this is one level, this is one level, and this one is one level. From this level to this level, there is a electronic transition possible. From this level to this level, and from this level to this level. So how many transitions are possible? Here, 3 transitions are possible. So what is the correct option? C is the correct option. The plot showing the magnetic behavior of oxy and deoxyhemoglobin dashed line. Oxy is solid line and deoxy is dashed line. Here, molar magnetic susceptibility and temperature. And here the graph is between chi m t and t, not chi m and t, chi m t and t. We know that for paramagnetic substances, if you take chi m and t, if you take, let us take graph between chi m and t, here there is a decrease in magnetic susceptibility with the temperature in the case of paramagnetic. In the case of diamagnetic, it is 0, nearly 0 or sometimes negative. There is no change with temperature. If you take chi-m T and T, this is the paramagnetic and this will be the diamagnetic. Let us take this as 0. This is the diamagnetic. This is para and this is diamagnetic. You have to identify oxy and deoxyhemoglobin. What is the magnetic nature of oxy? We know that oxyhemoglobin, HbO2, if you take, okay, all the electrons are paid, so this one is diamagnetic. Okay, when you release 1 mole of oxygen from HbO2, and there is a generation of 4 unpaired electrons. 4 unpaired electrons this one has. So it's a strong paramagnetic substance. So oxyhemoglobin is a diamagnetic, deoxyhemoglobin is a paramagnetic. So oxy is dia, the solid line should be diamagnetic. So here which one represents diamagnetic? This is dia. So HbO2, this one is oxyhemoglobin, and dashed line, this one is para. So this one is Hb. So what is the correct option here? A is the correct option. If chi-m and T is given, then C will be the correct answer. The major product formed in the following reaction is, what is the major product? Okay, in this case, what is the mechanism? Br, this one is double bond O, and this one is phenyl and methyl, and this one is bromine. Okay, when you add base, here the base is methoxide. So this one abstracts proton from this carbon. Here there is no, these are alpha positions to the carbonyl group. These are more acidic. In this case, there is no alpha hydrogen. Here there is a alpha hydrogen. So this alpha hydrogen will be abstracted by the methoxide. So you will get carbanion intermediate, double bond O, and bromine, and this is a minus charge, and this one is bromine, this one is methyl, this one is phenyl. This carbanion will attack on this SN2 type of reaction will be taking place. So here you will get 3-member ring, double bond O, and here there is a removal of bromine. So what is the compound you will get? Br, and this one is PHMe. In next step there is a attacking of methoxide. In this step there is a attacking of methoxide, MeO minus. This MeO minus will attack on this one. So these electrons comes like this. So you will get, this is this one is O minus, and this one is OMe, and this one is bromine, and this is phenyl and methyl. And these electrons comes like this, and then these electrons comes like this. These electrons moves like this, and this bromine comes out. Okay, there is a two possibilities. When these electrons comes like this bond can be moved, or this bond can be moved. In this case, there is a possibility of more substituted alkane. In this case, there is a formation of less substituted alkane. So this one is more favorable. So you will get pH, and this one is Me, and here there is a double bond, and this carbon is attached with This is the carbon. So this carbon is attached with OMG and C double bond O. So what is the structure? What is the structure you will get? PHMe double bond O, C double bond O, Me. Okay, which one is the correct option? A is the correct option. Okay, this one is it's a named reaction, Favorsky rearrangement. Yeah, this one is possible when there is a alpha halo ketones, alpha bromoketones. This rearrangement is possible in presence of base. So what is the correct option? A is the correct option. The rate of solvolysis of 1,4 follows. What is the rate of solvolysis? Here, in solvolysis, there is a dissociation of CX bond and there is a formation of carbocation. In SN1 reaction, solvolysis takes place. Here you have to identify which one can form more stable carbocation. Suppose as the stability of C plus increases, automatically solvolysis, the rate of solvolysis increases. So you have to identify which one is more stable carbocation. So let us write down which is what is the carbocation which is formed in this case. Okay, here when there is a removal of bromine, these pi electrons attack on the center. So here there is a formation of non-classical carbocation. This is a non-classical carbocation. In this case, you will get this is a carbocation and double bond. Here there is a removal of bromine, so you will get positive charge here. And when you remove bromine here, double bond, del group here, you will get positive charge. And this one, double bond, and here you will get positive charge. We know that third one, the cyclopropenyl cation, it's aromatic. This one is aromatic, and this one is non-aromatic. Here you have 2 pi electrons and planar, 4 pi electrons planar. It's a anti-aromatic. Anti-aromatic. We know that anti-aromatic are least stable, aromatic are most stable. Here, due to resonance effect and also hyperconjugation due to methyl group, this one is stable. So you can predict which one is the most stable. Most stable is what is the stability order? The most stable is aromatic compound, that is third one. The next one is stabilized due to resonance and also hyperconjugation, that is second one. And the next one is this classical carbocation 1, and the least stable we know that anti-aromatic, that is 4. So the order will be, what is the order of solvolysis? The solvolysis order will be 3 greater than 2 greater than 1 greater than 4. What is the correct option? C is the correct option. The most stable species in each pair of conformers are. Here you have to identify 1,3 interactions. Suppose if you take this cyclohexane derivative, in this case the bulky group at the equatorial position, at the axial position you have hydrogens. Okay, at axial positions you have hydrogens. Here there is a repulsion between hydrogen and methyl. In this case there is no repulsion. And if you take this one, Here there is a repulsion between very bulky group and hydrogen. Here there is a repulsion between hydrogen and less bulky group. So this one is more stable. Okay, one is more stable. Okay, one stability order will be 1 greater than 2. Suppose if you take this one, and this is axial position hydrogen, and this is the axial position hydrogen. In this case, there is no hydrogen at axial position. Okay, so here there is a repulsion between methyl group and hydrogen. Here there is no 1,3 interactions. Here there is no repulsion between methyl or tertiary butyl with hydrogen. So which one is more stable? Fourth one is more stable than third one. If you take this one, here OH, and here you have lone pair of electrons. We know that between oxygen and hydrogen there is a formation of hydrogen bond. Suppose if you take OH as like this, there is a formation of hydrogen bond when OH is at axial position. This interaction increases stability. Here there is an attraction force between the lone pair of electrons on the oxygen and the partial positive charge on the hydrogen. It's attraction forces, so there is a increase in stability. In this case, there is no such type of hydrogen bonding. Here, no H bonding. Suppose if you take these electrons will be like this. These electrons will be like this. So in this case, the OH hydrogen is far away from the lone pair of electrons, so there is no formation of hydrogen bond. So which one is more stable? Fifth one is more stable than sixth one. So what is the order? The most stable species in each one? 1, 4, 5. 1, 4, 5. So B is the correct option. The major product formed in the following reaction sequence is, we know that this reagent is used in McMurray reaction. This is a McMurray name reaction. So we know that if you take carbonyl compounds, 2 moles of carbonyl compounds, aldehydes or ketones, when you react with TiCl3CuZn, here there is a coupling between these two carbons. There is a formation of C double bond C, and there is a removal of 2 oxygens as TiO2. So in this case also, what is the product you can predict? You can predict this product. This one is OMe, double bond. This one is pH, and it can be written as, this one is CH double bond O. Here also another molecule CH double bond O. You have to take 2 molecules, and this is the pH, and this is the OMe. This is the double bond. This is the double bond. So in presence of this reagent, there is a removal of 2 oxygens and there is a formation of double bond. So you will get pH and C double bond C, and you will get this complex, this compound OMe, and here there is a double bond, and also here also there is a double bond and OMe here. Suppose if you take hydrolysis, acidic hydrolysis, H3O plus, so this OMe will become OH. So what is the compound you will get? pH, okay, C double bond C, and pH, here there is a OMe, OMe, and this is the double bond. This OMe will become OH upon acidic hydrolysis. OMe will become OH. So here there is a keto-enol tautomerization. The keto form will be C double bond O, and here there is a removal of a double bond. Here there is a hydrogen, and here also C double bond O, removal of hydrogen. Here hydrogen. So what is the molecule? pH C double bond O, CH2, C double bond C. Next to CH2, C double bond O, pH. So which one is the correct option? Which one is the correct option? This C is the correct option. Molecule. For the Diels order reaction 1,4, the activation barriers follow the order. We know that activation barrier means here activation energy. More the activation energy, more the activation barrier. We know that rate increases with the decrease in activation energy. Suppose when there is a decrease in activation energy, there is an increase in rate. In this case, it's a Diels-Order reaction. This one is this is diene. These are dienophiles. Sorry, this is diene. This one is dienophile. Dienophile is given. Here different dienes are given. This one also diene. This one also diene, and this one also diene. We know that when the availability of pi electrons is more, then the reactivity of diene is more. The availability of pi electrons, okay, the availability of pi electrons, it depends on resonance energy. Okay, less the resonance energy, more the availability of pi electrons. So in this case, which one has less resonance energy? Okay, the order will be, this is the order. If you take resonance energy, we know that thiophene has more resonance energy, and next one is this one, pyrrole, and next one is furan. Okay, all these are aromatic. Okay, this one is not aromatic, so this one has less resonance energy. So the diene which has less resonance energy, in that case there is a more availability of pi electrons, so there is a high rate and a less activation barrier. So you, in this case, what is order? Less resonance energy, more availability of pi electrons, more rate, less activation barrier. Suppose more resonance energy, less rate, more activation barrier. So the activation barrier that is EA is directly proportional to resonance energy of diene. So this is a sequence of resonance energy. So what is the order will be? What is the order? This is the third one, and this one is fourth one, and this one is second one, and this one is first one. So what is the order? Third one, fourth one, second one, and first one. This is the order of activation barrier. The major product formed in the following reaction is, so in this reaction, what is the intermediate? CO2H. Here normal bond is given. This is a double bond O. We know that when it is reacted with I2, there is a formation of a cyclic idonium ion. So this is a ion you will get. and this is a C double bond OH. C double bond OH. So here the OH, the lone pair electrons on the OH will attack on this carbon. This carbon is near to the OH. So you can write this way also. Okay, let us take this one. This one is this is I plus, and you can write OH like this. Here this is the attack of OH. So these electrons come like this. Here SN2 type of reaction will take place. We know that in SN2 there is an inversion of configuration. Suppose if this COOH group attacks on this carbon from above the plane, then this bond will be above the plane. This bond will be above the plane. Suppose when this is above the plane, this one attacks on this carbon or above the plane. So you will get and this one I will be below the plane. When COOH attacks on this intermediate on above the plane, the I should be below the plane. So which one is the correct option? Suppose if you take option A, this one is above the plane. When this one is above the plane, it should be above the plane, but this should be below the plane. Since it is SN2 type of reaction, it should be below the plane. So this one is not correct. This one is above the plane. Obviously, this should be above the plane, and this one should be below the plane. So this one is correct. Suppose if you take this one is above the plane, this one is below the plane. This is not possible. Okay, when COOH is above the plane, it cannot attack below the plane. It cannot attack. In this case also, this one is above the plane, and here below the plane. It is also not possible. So what is the correct option? B is the correct option. In coming video, I will explain remaining questions in JAM 2020 chemistry paper. Thank you. Subscribe the channel, share the videos, and if you have any doubts, please post a comment in the comment box. Thank you.